Swayam Prabha. Digital India. Educated India.
Okay, so let's get started. We have been looking at division of discrete goods, looking at division of indivisible goods, and our sort of fairness notion is NV freeness up to one good, EF1. This is our solution concept of choice, and our goal is to see and establish the existence, the universal existence of this notion of fairness in as general a setting as possible, and more ideally, in fact, develop an algorithm that finds such an allocation efficiently. So, just to recall, so a solution here, the output of the fair division exercise has to be a partition of the goods into n subsets, where n is the number of agents. So, every agent gets a subset of goods. These goods, of course, have to be pairwise, these subsets indeed have to be pairwise disjoint. So, a good goes to exactly one agent, and so such a partition, such a allocation is said to be EF1, is deemed fair under this definition if and only if the following condition holds, that if I look at any pair of agents A and B, then there is a good G in the second agent's bundle in the subset assigned to agent B, i.e. in AB, such that if I remove this good from consideration, so I look at, instead of looking at AB, I am looking at a set where this good has been removed out, then A values its own allocated subset AA more than this modified subset. So, up to one good, up to the removal of one good from the other agent's bundle, A is sort of happy in the sense of this particular inequality holds for A. So, as with NV freeness, we are looking at VA on both the left hand side and right hand side of inequality. The key difference is I am allowing you to remove one good out. Okay, so with that, we kind of went through patiently over this example where the valuations were additive, and what we did was followed like an iterative process. We iteratively assigned goods one after the other, and what we could accomplish in this example at least was the fact that if we looked at the NV graph at every stage of the algorithm, at every iteration, again, what is an NV graph? Well, we looked at the partial allocation we have so far, and we drew edges that pointed to NV among agents. So, it's a directed graph where nodes represent or correspond to agents and directed edges signify NV between them. So, as we ran through this procedure, as we ran through this example, we could always find an agent that was a source in the directed graph, and by the semantics of the construction, this source vertex was corresponded to an agent that no one else envied. So, you looked at the source agent, what you had was at every point of time no one else envied the source agent, and our rule of choice, the sort of thumb rule that we followed, was always give the next good, assign the next good to such a source vertex, to this vertex that is not envied by anyone else. And indeed that's a good rule, and let me argue again to you why that's a good rule, in the sense that if I do follow it along, then I will continue to maintain EF1. So, what I am saying is that initially I started with empty allocation, so everyone had just the empty set, these AIs corresponding to all agents were empty, so that's NV free and hence EF1, and what we are going to do is maintain this property inductively. We are going to maintain it as an invariant, and this rule that I just outlined accomplishes this task, and let's sort of go over it one more time to sort of hammer it in. So, at any stage, say I look at the NV graph, and at that stage, say by luck, so it's sort of this is a special case, if you will. Again, there could be NV graphs where there is no source, but let's worry about that later. For now, I am saying say that your NV graph does have a source vertex, i.e. there's this agent I that no one else envies. And what we did in this procedure throughout was we took the next good, let's say G, and assigned it to agent I. That is, we started with AI, whatever the current set of goods that were given to I, and then included G in it. So essentially said, okay, here you go, agent I, this next good G is yours. And the point was that this sort of an update, this allocation of good G to agent I maintained the EF1 property, and that's what I want to sort of argue here quickly. So observe that what ended up happening in this iteration, in this stage of the algorithm, was that I's bundle, the subset received by I, which was earlier AI and now it is AI union G, has this new good. For every other agent, J that's not I, the bundle remained as such. Like you didn't do anything, there was no update. But before the update, I had this particular inequality. If I looked at the agent J, so again, both sides, left hand side and the right hand side here, are with respect to J's valuation, then I had this inequality. Why? Well, because J was not envying I. No one was envying I, hence J was also not envying I. So this is the inequality I had up front. But note that if I now look at the new AI, which is AI, the old AI plus G, and I remove G out of it, what I get is the old AI, right? For some set I included G, I removed back, I'm back to the old AI. So this inequality here, this thing that I'm trying to put a box around, is nothing but the previous inequality with the new set of allocations, because AJ didn't change and AI just got one more good. So this is for all J, for all agents J that are not I. So in particular, this means that if I had an EF1 partial allocation, then even after I assign the next good, the new partial allocation that I have will continue to be EF1. There's one case that I have overlooked, which is what? So I need to also argue that it continues to be EF1 for I, right? So what this means is that if I look at AI, let me just write new to denote, this is the old, so yeah, this is just a rough notation. So this is what happens in the update, the AI gets you include G in AI. So what you would want to argue that EF1 continues to hold inductively. So if it held for the previous partial allocation, it's true. But that's sort of direct, because if you look at the new AI, you have one more good, right? So the only property I'm assuming here is that the valuations are monotonic, right? So note that what I have argued so far is extremely general. There's no place I have made the assumption that the valuations are additive. I have assumed nothing about the structure of the valuation except for this inequality right here, where I am assuming that the valuations are monotonic. But as far as assumptions go, this is a very generous assumption. This says, okay, if your valuations are monotonic and if you assign your subsequent good to a source vertex, to an agent who's not envied by anyone else, EF1 will continue to hold. So if you had EF1 in your previous iteration, you'll have EF1 in the subsequent iteration. So just to sort of complete this, this is by this, and this is the sort of inductive hypothesis, i.e. the fact that in the previous iteration you had EF1. So this is So for all j, there exists some, let me just call it say g hat to separate it from this good that's assigned. So this is because like before you assign this good g here, you had EF1 and so inductively it kind of marches on. So you had EF1 yesterday, you will have EF1 today, yada yada yada. So that's the sort of simple but crucial observation. Why aren't we done yet? Like why is it like why don't I have what sort of the thing that's missing is that I am still relying on the fact that as I march on through this algorithm, every time I will have a source vertex. At every point, there will be one way or the other, there will be a vertex that I can happily assign G and sort of invoke this observation. So this is something we need, and as I said, we in this case we make our own luck. We'll actually observe something that will allow us to find such a source vertex, find a agent that will be the recipient of the next good, find an agent that's not the source, like will not be envied by anyone else as the sort of algorithm progresses. So let's try to do that before I march on and sort of write a pseudocode or anything, like define things a bit more formally. Here's the sort of theorem. So you give me any discrete fair division problem, that is, you give me a problem where the goods are indivisible. And as I said, the only assumption, and it's a very sort of minimal assumption I'm making, is that the valuations are monotonic. Like if you actually look around at other sort of related concepts, getting something at this level of generality is typically quite hard and invariably impossible. There are negative results. But for this EF1, this is spectacularly general result holds, says that all you need are monotonic valuations. All you need is the fact that if I give you a bigger set, if I look at a superset of something, your valuation does not decrease, right? And it's exactly used here in the observation. But I'm saying all I'm going to do is sort of use this assumption. If I increase your set, the valuation, increase it in a containment sense, then the valuation does not decrease. So the first statement of this theorem is existential. It says that as long as you have monotonicity, an EF1 allocation, a fair allocation in this sense, is guaranteed to exist. And again, I am writing this as two separate statements to like emphasize the fact that there is a existential result here as well as an algorithmic result here. In fact, the way you get this existential result is through an algorithm, and So again, I'll not go into the details of it, but when I say efficiently, I mean efficient in a query sense. So think of running this algorithm with n agents, and every time you have to evaluate the value of a subset, you just query the guy, okay, if I were to give you this, what's your value? So you have something analogous to, say, the eval queries, like modified appropriately for the discrete setting of the Robertson Web model, for the very natural query model. When I say you can do it efficiently, effectively means that you'll only bother the agents a polynomial number of times before finding an EF1 allocation. So you certainly don't need to look at all the values for all the 2 to the m subsets for any agent. And again, like something that one should appreciate as computer scientists are the gaps between 2 to the m and poly, right? For 1000 or 2000 value of m, if you have 2000 goods, the value between 2 to the power 2000 versus 2000 square is a population of Ahmedabad versus number of stars in the universe. So these are drastically, instead of you have a function that's that complicated, right? It's that huge. Its specification would require you to spell out 2 to the m values. You are able to obtain a result for such general functions. Only property is monotonicity. For such general functions in a polynomial, by looking at it at a polynomial number of places, this is indeed impressive. Right? It's like almost being able to find one right individual by just looking at 10 people in India or something. This is that part, like the comparison should be stark and impressive as CS computer science students to us. Okay, so having sold this result enough, let me move on and systematically write down what we have done, and in particular define slightly more formally what the NV graph is, prove a property about the NV graph, and then we'll come back to the algorithm. So one sort of another comment here, note that the way we actually get to the algorithm is by establishing mathematical properties about the problem and related constructs. This is one place where the first kind of the generic statements I made early on, that these mathematical analysis is not an afterthought, it actually is a guiding light. Here, the way you are able to get to this algorithm is by actually understanding mathematical features of the problem. So this is again an important aspect. It's not a liability that I actually know the right algorithm, I just for passing the course, let me try to figure out a proof. No, in fact, it's a much simpler case. There are many more revealing examples where the mathematical machinery or the key ideas actually are critical for designing the right algorithm. Again, I hope a flavor of this sentiment gets conveyed in this particular exercise as well. So the construct we are looking at is this NV graph. So this is a directed graph with so you have a vertex in this graph, in this directed graph, for every agent. So every agent you put a vertex. It's simply the idea that you just put all the agents in a room and ask them to point to people who they envy. And so let's note that I'll define this for as the algorithm progresses, I have these subsets for different agents, AIs, but they are disjoint, so they are pairwise disjoint, but the union is still not equal to M. I have only assigned some, so at some point I had only assigned the first good, the first 4 goods, and so on. So these are partial in the sense that they do form like they are disjoint and they sort of correspond to like AI goes to agent I, but the word partial here emphasizes the fact that the union is still not M. I am still progressing towards a full allocation, an allocation where every object, every discrete item among the M items gets assigned. So that's the word partial here is just to emphasize that. And for every partial allocation, I can define this thing. So this here is a definition. This is a definition of this object that we are studying. So the graph has, say, some vertex set which is nothing but this, and I have a set of arcs, a set of directed edges, and here the point is that I look at a edge between two agents, two vertices I and j, and this is included in the edge set. So this is a directed edge if and only if, so I and v is j. Right, and this is the condition for NV. I looks at its own current bundle, the AI, and says, you know what, I would actually prefer J's. So if this happens, you put a directed edge between nodes I and j that represent agents I and j respectively. Okay, so yeah, this we have already seen. If you like pictures, here's the NV graph towards the end of the process that we followed for the example. Here agent 2 is NBS of agent 1 and 3. So you have these two directed edges with a directed graph with 3 vertices, 3 agents. Agent 1 and 3 are sort of satisfied. They are in fact sinks in this directed graph. Right? They don't envy anyone. So this is nothing but a general. So instead of 3, I have n agents, and instead of one, like for any partial allocation, I can define this, and I hope I don't have to like sort of convince you that this is a good object to study. It at least was very helpful in the previous example. I just now took that idea and generalized it, defined it more generally. That's all I have done. Okay, so now comes the crucial lemma, the missing piece of the puzzle, and I'll call it the shuffling lemma, and you'll see why this choice of words. And the lemma says that so I give you any collection of subsets, they are disjoint, associated appropriately with agents, so but they might or might not cover all the M elements. But you give me any such partial allocation, what I can do is I can shuffle these subsets around, and I'll explain properly what that means. So the idea is, okay, you give me any partial allocation, you give me an assignment of subsets to agents, I'll look at this assignment, and what I can do is, okay, I'll say, I can shuffle them efficiently, that is, I'll say, okay, let's exchange I'll pick a few agents, say 3 of them, and I'll say, okay, the first agent bundle goes to the third agent's bundle goes to the second, and the second agent bundle goes to the first one. So I can shuffle them around. So still, I just reassign these bundles, if you will, such that the new, potentially new partial allocation I obtain has 2 very nice properties. The first one is that no one gets angry, no agent actually gets angry with this shuffle, in the sense that for every agent, possibly the new bundle it receives. So for an agent, the bundle might not change. If it does change, if it, say, agent 7 receives the bundle of agent 3, but even after this shuffle happens, the value of the agent does not decrease. This is true for all agents I in N. Right. So note that I am not changing the ingredients of AI. What I am going to do by shuffle, I mean literally a reassignment of these subsets A1 through AN among the agents. So such that with the new reassignment, I have this property. So again, in the partial allocation, the BI's agent I gets BI. Right. So okay, my first question to you is that if I stop the lemma here and do not look at the second condition, I would have just wasted 2 minutes of your time. Why is that? Or 2 minutes of my time. So if I ignore this second part and I say that the lemma is I can always do this efficiently to satisfy just condition 1 in isolation, why is this not worth you coming back from lunch? What is that? Forget this source thing. I'm saying just read the lemma and stop before this and appears. So stop before bullet point 2. Do I have to change anything to actually satisfy? I just keep A as is. Do I get this property? Forget G. I mean, if you look at the first part, like if you ignore, I don't want to erase this, but let me erase this. I'm saying here's a lemma. It does not refer to the NV graph at all. It just says blah. I'm saying this is it's a bad question, not just a bad lemma. Even just asking this is not. What is that? Yeah, A satisfies it, right? I mean, fine, you just keep it as is. Everyone is greater than equal to, so if it's equal to for everyone. So it's a triviality, so fine. You, in and of itself, this is nothing worth thinking about. What the nice property here is that this new B that you get, if you look at the NB graph with respect to this new partial allocation, so note that this definition is with respect to partial allocation. So A is being overloaded. The definition also is meaningful when I look at it's a definition for all partial allocations. This says that if I look at the NB graph with respect to this, then this is in fact acyclic. And that's the important point, that's the sort of crucial aspect of this construction. So the proof of the lemma is actually, yeah, let me go up. So say, I mean, we were looking at 3 agents here. This was my example. Again, it was curated to ensure that I always had a source. Say that wasn't the case. At some point, what ended up happening, let's say I picked the numbers and I changed things such that, so say with 3 agents, at some point what ended up happening was agent 1 was envying agent 2, agent 2 was envying agent 3, and agent 3 was envying agent 1. So I have some partial allocation where the 3 agents are getting A1, A2, A3 respectively. But this partial allocation gave me an NV graph that was a cycle, right? So in particular, it's not acyclic, there is a directed cycle. My question to you, what's a simple idea I can employ to get rid of this cycle and achieve the lemma? Yeah, just shuffle, like go in the opposite direction of the cycle. What you do is, okay, you look at A3 and you now assign it to, look at A1, assign it to 3. So what you do is, look, B3 becomes A1, you move in the opposite direction, fine. A3 is actually happier, right? So this NV edge, what did it mean? It meant that when V3 was looking at A3, this was less than the V3 for A1, right? This is the condition that forced you to put this directed edge right here, and so on and so forth. So my suggestion is, let's just go, like, traverse the cycle in the, yeah, like a true Indian, we go in the opposite direction of a one-way lane, and so reverse the cycle. So fine, B1 becomes A2, you kind of swap, and B2 becomes A3. So that's the update, that's the shuffle I perform. I just give every edge. So I am envious of you, I'll get your bundle. Someone else is envious of me, that person gets my bundle, and it kind of repeats. Is the process clear? So I just, yeah, rotate the cycle, if you will. But note that because of this inequality, so what I have done is B3 is A1, right? I shuffled these two subsets. So I have equality here. This is just a notational change. I'm calling B3. What was A1 is now being called as B3. So I have this, and this is the first strict inequality is because of the NV condition. So if I do this, certainly the first condition of the lemma continues to hold. Now looking at the second condition, the point though is that what you have done is you have looked at the graph and actually killed off one cycle. Once you do this reshuffling, agent 3 will not necessarily continue to NV agent 1, at least in this example. Right, so this is just an example. Let me write down the whole thing a bit properly. So proof is, so the idea is you start with a partial allocation A1 through AN, and if you look at the NV graph induced by this, if this is indeed cyclic, then sort of shuffle the subsets So you do this cycle resolution. I expressed it for 3 agents, but let's say the cycle is of k agents, nothing changes. You just kind of go, keep passing the subsets along, and that's it. This is sort of the idea, and I'll leave it as an exercise for you to argue that whenever you do this, the number of edges in the NV graph, so you started with A, you did this resolution, you got some other new partial allocation B. If you look at the NV graph of this new partial allocation B, the number of edges, directed edges, would have decreased. So So from this A partial allocation, you sort of resolve the cycle, you say got another partial allocation B. The claim that I'm leaving it as an exercise is that the number of edges in the NV graph corresponding to this new partial allocation is less than the number of edges in the NV graph for the original, the partial allocation that you started with. In particular, this cycle has gone. The NV edges are gone. So what this tells me is that I cannot keep doing it over an infinite number of iterations. So every time I do this, the number of edges drops. The number of edges can be at most order n squared to begin with. It's a directed graph with n vertices. So after a poly number of steps in poly time, the number of edges, you would have to be at a graph, you'd reach a partial allocation where there is no cycle, there's no cycle to be resolved, i.e. the graph is acyclic. You reach a final partial allocation B where the NV graph is free of cycles. So from A you go to B, you look at the NV graph, if there's a cycle you again repeat, rinse, repeat till you finally get to a partial allocation where there is no cycle. You have reached a place where the lemma holds true, and know that the first property is again sort of an induction. It's a property that continues to hold. Every time you do the cycle resolution, no agent's value goes down, right? So stitching these observations, what you have is a proof of this lemma. So we had an idea. The idea worked when I had source vertices in the NV graph, and now in parallel I have proved to you that I can always make the graph, this NV graph, acyclic. So this is almost without loss of generality. I can work with an allocation where the graph has no cycles. How do I merge these two ideas together? Yes, yeah. So again, repeat myself. When I say the allocation is partial, I mean not all goods have been assigned. So I could have, again, it would have become a bit of a hairy example, but like say I could have been in a stage where I'm here, so G1 is still not assigned, and so this is my partial allocation. So A1 is this, A2 is G4, and A3 is G2 and G3. If I have a cycle, I could have shuffled these bundles across the agents to now get another partial allocation. In fact, a partial allocation is where the subsets actually just remain as is, the owners changed. But in this new partial allocation, there was no cycle. Right. So, okay, how does acyclicity help me? Okay, before I go to acyclicity, I skipped a particular detail, which is, I left this part as an exercise. Again, it's a instructive exercise, so I do welcome you to finish it offline. But assuming, like having faith in this lemma, trusting it as is, what is the nice property about acyclic directed graphs? Okay, let me ask a related question. Give me an example of a directed graph that has no source vertex, i.e. a directed graph where there is no vertex, where all vertices have an incoming edge. A cycle, fine, but I have an acyclic graph. So can I argue that directed acyclic graphs always have a source vertex, i.e. So my observation to you is that if you give me any directed graph that is acyclic, it does not contain a cycle, then it must necessarily contain a vertex where there is no incoming edge, i.e. there has to be a source vertex. What's the argument? This is a 4-letter word I am looking for. And we have seen it in Sperner's lemma. Perfect. It's a path argument. Right. The idea is, okay, pick an arbitrary vertex. Your graph is acyclic. Two possibilities. Either this vertex has no incoming edge, in which case you are done. Otherwise, the vertex has an incoming edge. So you go to the predecessor, you go to the vertex who's pointing to it. Fine. Now you are at a new vertex. Repeat. So you are sort of following the path, but breaking this sort of, in fact, going in the opposite direction of these one-way roads, as we typically do. So you keep on doing this. It's a finite graph, and you'll never cycle back. That is, you'll never reach back to the vertex, any of the vertices that you have encountered so far. So this is a path argument, right? It's quite similar to the room following argument that was employed in Sperner's lemma. And this is a fairly, it's not a technically deep observation, but it is a very interesting observation that the existence of EF1 actually rests on this total argument. So whenever you see an existential result, whenever you see something like blah always exists, it's very instructive to actually pinpoint the seed, very instructive to actually find out what is it that's guiding the whole thing, what's under the curtain here, what is the root idea that kind of branches into this big messy tree. The root idea here is exactly this observation. So the universal existence of EF1 allocation actually rests on this simple graph theoretic idea that every acyclic graph has a source. So this existential result with some bunch of work translates into another existential result. Existential result for EF1 stems from this idea. So it's an important idea, it's an important enough idea that there's a complexity class associated with this. It's called PPAD. That's for another day, another week. So yeah, this is sort of not just a observation in passing. This does lead to some very deep interconnections. But getting back to the point at hand, let me just repeat it one more time. So the proof of this note, this observation, is that your graph is acyclic. So you start with any vertex I. So if it's not a source vertex, i.e. there is an incoming edge, it's an edge like this, then you go to the vertex that's pointing to it. Right, you are now at a new vertex, fine. You again keep following this path. The acyclicity means that at no point of time you will get to a situation where you get back to I. Right, if you are because then that's a cycle. This cannot happen. There's a finite number of vertices. At some point of time, your efforts you will succeed, hard work will pay off, and you will have reached a source vertex, you would have reached a vertex where there is no incoming edge. Okay. Fine. So far so good. Now can I stitch everything together? Yes. Yes, yes, yes. Yes. So it could happen, like again, I kind of, this is the part of the thing that I left out as an exercise. So this claim, but you're right. I mean, of course, it can be the case that so you are at a partial allocation A. Your NV graph looks like this, and there is this isolated. So you have 6 agents. Your NV graph is like this. There are 2 of them that don't care. There's a non-vegetarian buffet. These guys are envying each other's plates. The 2 vegetarians who are happily sitting away. So what you now do is like resolve, and okay, so this guy is actually envious of this. This guy has a nice dessert, say whatever. So you could happen, now what you'll do is, let's say this is A1, this is A2, A3, A4, A5, A6. So the subscript denote both the vertex, agent identity and the thing. So when you'll do the shuffle across the cycle, A1 will end up here, right? So this guy now owns A1, this guy will own A4, so on. So it might happen that this guy still now starts envying A5. So this edge that's not part of the cycle might persist on, fine. But I'm saying that no new edges, like no totally new edges will, the total number of edges will kind of strictly decrease. In particular, you would have removed these NV edges, but it does require an observation looking at all of these scenarios, and that's why I kind of didn't go. I mean, if you sit back and stare at it, you'll see that indeed, I mean, edges like this one might get shifted around, but no new NV edges. Sorry, the number of edges will sort of strictly decrease, and that's sufficient for you to argue that it will terminate in polytime because you started with a polynomial number of edges. Again, yeah, so this is an aspect that I haven't, like, in the interest of time, not sort of flushed out all the details, but these are just details. Now, there's no fundamentally involved idea here. So I have 2 observations so far. The first one is that if I have a partial allocation and the corresponding NV graph has a source vertex, giving the next good to this source vertex maintains EF1. That's the reason why I soldiered through that example. The second observation is that I can do a bit of reassignment and always ensure that the NV graph is acyclic, i.e. it has a source. Armed with these 2 observations, I have an algorithm, and this is, I'll refer to as the trading cycle algorithm. The name here comes from the fact that there are connections with this and something called the top trading cycle. It's a old work by Gale and Scarf, but yeah, if you're interested, I can sort of talk about the connection offline, but that's some other classical work in sort of microeconomics. So it's just, the name is just to say that I perform these shuffles across cycles, hence that's sort of, it's one choice of calling the algorithm something. So let me just spell it out. So again, what I'm going to do now is pretty much what we have discussed so far. I'll just write it down for completeness, the entire pseudocode, so it's clear, it's there in black and white. So I start with the empty partial allocation, everyone gets nothing, and I'll also initialize so I'll keep track of the goods that are unassigned, and it's an iterative process that as I move along, I'll reduce this set capital M. So I'll keep on removing one good after the other. So keep assigning. So this is the set of goods that are unassigned at any point of time. Initially, everything is unassigned. So M is the set of all goods. And you also look at the NV graph G with this, so partial allocation A1 through AN, which is this, and So initially everyone has the empty set, there is no NV edge, it's just a graph of isolated vertices. So that's your initialization, and you kind of iterate till you have assigned all the goods. So you iterate till there's some good left unassigned. I mean, the arbitrariness of this algorithm is sometimes intriguing, in the sense that I'm actually going to pick any good. Right? That really does not matter. I don't even have to look at a choice. I just have a whole bunch of things in my Santa Claus bag. I'll pick anything, and I look at the guy who's sort of not the sort. No one is envying this person. It's like a poor kid standing in the corner, and I'll give the next good to this guy. I'll update my envy graph, shuffle these cycles around, and march on. So AI is the source vertex I have selected, and G is literally the arbitrary good which is currently unassigned. It's currently in this set M. So I'll assign, and also, like, now that G has been allocated, I'll remove it from consideration. That's the thing. I'll shuffle A to sort of, if required, to ensure that GA is acyclic. This is just, remember the lemma that this does not decrease the valuations, and I can do it, execute this step following this lemma in polytime such that this is necessarily obtained. Once I have acyclicity, it means that this particular step here can be always successfully executed. Acyclic graph will necessarily have a source vertex, so the algorithm will march on, and finally I'll just, when this set becomes empty, I've assigned all the goods. I in fact have a full allocation, not a partial allocation. Just return it. Super elegant. A piece of art here. Yeah. Why is this going to run in polytime? Right. So there's m goods. Just so linear in the size of the inputs. So the loop will iterate at most m times. Every time you do, you remove a good from m. So the iteration count here, this while loop will iterate, will execute at most m times. In every loop, you are going to invoke this lemma, which is again a polytime thing. It's a cycle resolution is a efficient subroutine. There you go. It's a, right off the bat, it's a very efficient algorithm. My claim to you is that, yeah, this indeed establishes, which will now kind of do, is it will establish this theorem. It will prove that there is always an EF1 allocation, and all you require for it is monotonicity. And this is almost it's just a repetition of like what I've said. In fact, things that I've said at least twice or thrice. So still, for completeness, let's do this. So what is this proof of? It's a proof that this trading cycle algorithm, this algorithm right here, is actually going to find an EF1 algorithm, and I've already argued that this runs in polytime. If there's a question about how the algorithm works, it's a good place to ask. Otherwise, we'll kind of see the sort of argument for a final time.